Hello all, we are going to see the explanation for the experiment determination of the dissolved oxygen. When we say dissolved oxygen, that it means that this particular oxygen will be dissolved into the liquid. So normally what we inhale is the atmospheric oxygen, and we particularly take the oxygen from the atmosphere for our metabolic activity. Similarly, this dissolved oxygen also has some significance, and it will be covered in due course of this lecture. Let's start with the introduction to the topic. The atmospheric oxygen that we have in the atmosphere is not readily soluble in water. You all know that the atmosphere is the envelope of the gases that is covering the surface of the earth, and the atmosphere consists of different gases. The most dominant gas is the nitrogen, and the second most dominant gas that we have is the oxygen. So all these gases put some pressure on the surface of the water, maybe the water body in the river, oceans, and everywhere, all the water bodies, and they, because of this because of the partial pressure of this gases on the liquid surface, these gases get dissolved. So the solubility of these gases in the liquid is directly proportional to the partial pressure. So this is the Henry's law. Henry's law state that the amount of gas that is going to get dissolved in the water is totally dependent upon the partial pressure that is exerted by the gas on the surface of the liquid. So for example, at a specific temperature of like 20 degree Celsius, and the Henry's law's constant being 43.8 mg per liter. So and the atmospheric and the for the partial pressure of oxygen to be 0.2094 and the atmospheric pressure to be 1 atm, we can find out the DO saturation value at 20 degrees Celsius by putting into the values, that is 43.8 into 1 into 0.2094 comes out to be 9.17 mg per liter. So now this is the DO saturation value. DO, as you all know, is the dissolved oxygen. Let's understand what is the meaning of DO saturation value. The DO saturation value is the maximum DO value in mg per liter for a specific temperature. So if I consider the temperature to be 0 degrees Celsius, then the DO saturation value is 14.62. So that means that at 0 degrees Celsius, I will be getting the maximum value of a DO present as 14.62. I won't be getting the DO value greater than 14.62 at that particular temperature. So indirectly, I'm also making you understand that the DO saturation value is also a temperature specific phenomenon, right? So now this DO saturation value gets affected by various factors. Factors listed are DO saturation value decreases with the rise in temperature, it decreases with the rise in salt concentration, decreases with the rise in altitude, and rise in organic concentration. So all these temperature, concentration, altitude, and organic concentration value, if are on the higher side, the DO saturation value will be definitely on the lower side. So we are going to understand why this is the case and how the DO saturation value also varies for all these different aspects. Let's concentrate on table 1, where we have variation of a DO with the temperature. So if I have a clean water at a 0 altitude and at 1 atm pressure, so that means if I'm at 0 altitude, I'm at 1 atmospheric pressure. So these are the DO saturation value with respect to the temperature. So temperature, if my temperature is 0 degrees Celsius, as I earlier said, the DO saturation value in mg per liter is 14.62. Similarly, if it is 5, then it is 12.80, and if you go on increasing the temperature, here you will be seeing that the DO saturation value goes on changing. So if you see the for 50 degrees Celsius, the DO saturation value is 5.60, which is far more less than 14.62 for 0 degrees Celsius. So why this is happening is also the matter of discussion, right? So when we increase the temperature, from this relationship we can see that the DO saturation values are decreasing. But why these values are decreasing, that needs to be understood. All right. So if we see the water is no, the dissolved oxygen is the water is made with the help of the hydrogen and the oxygen molecules, and also the oxygen, the dissolved oxygen is present in the water. So there is structural and the dissolved oxygen both present in the water, right? So when we start heating the water, what will happen is that the soluble oxygen in the soluble oxygen in the water will start to get liberated. There is also the loss of structural oxygen that is present. So both structural oxygen and the dissolved oxygen that is going to get liberated. Now, why it is getting liberated? If we have, if you know, the structural oxygen has a bond with hydrogen, and with increase in the temperature the bond will get weaker and weaker, and no at weaker and weaker, and at temperature, at a suitable temperature it will break and releasing the oxygen. Also for dissolved, when we say that the oxygen is dissolved, it is also with no, it is having some bond with the entire water, and that particular bond get reduced when the temperature increases. And as the temperature increases, what will happen, all this oxygen in some in the form of dissolve, and some in the form of structural oxygen will get liberated, decreasing the DO saturation value, right? So we should keep in mind the DO saturation value will go on changing if we increase the temperature. So at a higher temperature, less DO saturation value will be observed, right? Now table number 2 depicts about the variation of DO with the salt concentration. So here we have considered chloride as a salt, and we have considered that the chloride concentration in water at 1 atmospheric pressure is taken into consideration. So if we take a temperature, let's say 10 degrees Celsius, so at 0 mg per liter, we have a value of a DO saturation as 11.33. Now let's start increasing the chloride concentration and no, and get focus, and let's focus upon the DO saturation value as well. So if I'm increasing the chloride concentration to 1000 mg per liter, what happens next is that my DO saturation value get decreased. It happens to be 11.21. Similarly, if I'm increasing the concentration of chloride to 5000 mg per liter, so the DO saturation value changes to 10.74. And similarly, for 20,000 mg per liter of chloride concentration, the DO saturation value comes out to be 8.98, right? So if we concentrate upon the trend, we'll be getting to know that as the salt concentration increases, the DO saturation value will go on reducing. When I say that DO saturation value is changing, it also means that the DO value is also changing. Now let's focus, or let's understand why this is happening, right? So if I'm putting some chloride into the water, now here chloride, you can take sodium chloride, that is NaCl, or the salt that we have at home, and when we when we put this salt in the water and try to stir, what will happen is that the salt will get dissolved, right? So when it is getting dissolved, it will be reacting with the dissolved oxygen that is present in the water. So when it is acting with the dissolved oxygen, what will happen, it will be utilizing the dissolved oxygen, and the quantity of the dissolved oxygen in the water will get reduced. So higher is the chloride concentration, what is going to happen is that there is the dissolved oxygen utilization, and as there is utilization of this dissolved oxygen, the DO saturation value, or the DO value of that part of water will get changed, right? So similarly, the same trend of reduction in the DO saturation value is observed for all the other no, for all the other temperatures. So the relation remains same. So at a given temperature, at a given pressure, if the chloride concentration is changed, the DO saturation value is going to be changed, right? So now for taking a practical example of it, if I've found out the dissolved oxygen content in the river water which is flowing in Pune, and if I try to compare this DO value with the DO value of the DO value of the uh, ocean, or the DO value of the water sample collected from the ocean at Gateway of India in Mumbai. So you will be, after understanding this relationship, you will be definitely telling me that the TO value of that water which is collected from an ocean at Gateway of India in Mumbai will be less than that of the DO value of the water which is collected from the river in Pune. Why? Because we have collected a sea sample of a sample which is consisting of lot of salts. It is a saline water, and saline water will have definitely have the less DO, which is less DO than the water which is freshly flowing in the river, right? So this was the relationship of DO with the salt concentration. Let's move ahead and find out what is the variation of a DO with altitude. Right now, we have to understand what happens with the altitude, right? So what is the effect of the altitude on the oxygen concentration in the atmosphere? So when I'm at a normal altitude, what is going to happen is that the density of the air is on the higher side, right? So as my altitude is going to increase, the density of the air is going to decrease. When I say that the density of the air is going to decrease, that means that the concentration of the constituent gases in that air will, now what it will no particularly it will also decrease. So when I say that concentration is going to decrease, that means the nitrogen and oxygen will be available at that particular stretch as well, but they will be in this scarce quantity, right? So the density is decreasing, that means that particular, the quantity of the gas in for a per volume will be going to decrease. So oxygen will be available, but the oxygen atoms will be, no, they will be scarcely present in that particular air unit, and no, at that particular time we won't be getting the enough amount of oxygen. The same happens if you have to take an example. At a normal altitude, I do not require an oxygen cylinder to inhale the oxygen, right? So enough concentration of oxygen is available because the air density is more. So when I climb towards, no, when I climb, for example, I'm at Mount Everest. So you'll be seeing that the mountaineers carry the oxygen cylinder while they are, while they are climbing the Mount Everest. So why so? Because the air density reduces and the oxygen comes, the concentration of the oxygen reduces. The oxygen is present, but the concentration is less. The quantity is less. That is, no, the quantity is very less than that required by the human body, and hence we required the oxygen cylinder. So the relation we already know, the variation of no DO with altitude, we have already seen, that is the DO value will go on decreasing when the altitude increases. So if we say I'm at temperature 15 degrees Celsius and I'm at altitude 0 meter. So the DO saturation value is 10.15, and as my altitude increases, what will happen? The DO value will go on decreasing. So at altitude 3000 meter, you have the DO value to be 6.98. Right. So for all the temperature ranges, these DO values are already given. The value of P0 and P can be found out by the formulas or the description that has been given here. So you, by using this particular, if I'm knowing what is the altitude H, I can find out the value of P, and no, same can be used for determining the DO saturation at that particular value. So this was just an example to tell you how the DO value changes with the change in the altitude, right? So now nextly, a very important factor that we have seen three factors: rise in temperature decreasing the DO saturation value, rise in salt concentration decreasing the DO saturation value, rise in altitude decreasing the DO saturation value, and lastly we have rise in the organic concentration, right? So organic concentration, particular, no, we all know what is an organic substrate. Normally when we have an household, normally when we consider our household, the organic substrate in the form of solid waste, in the form of food waste, and food waste and all those things go into that is nothing but the organic waste. Even the waste that is coming out of the toilets and the WCs is also considered as an organic waste. And no, normally if we do not treat this water, sewage, so what will happen is that the sewage will get dumped into the river body. So what will happen? The organic, when we are dumping the dumping the liquid waste, that is the sewage from our household into the river body, we are increasing the organic concentration. So you'll be you must have read in many of the newspapers that the river is getting polluted. So when the river is getting polluted, that means that the organic concentration or some like no, even the inorganic concentration is increasing. But we are not going to focus upon inorganic concentration here because of our activity, because of the sewage. The organic concentration is going to increase, and because of that, the DO will decrease. Why the DO will decrease? Because the organic concentration require no the organic substrate requires to go the aerobic degradation, and for the aerobic degradation or the aerobic biodegradation, we all know the oxygen is required. So the organic substrate will be utilizing the dissolved oxygen in the water for its own degradation process. And with no because of that, the concentration, because of that, the dissolved oxygen value in the substrate in the water will go on decreasing, right? So which is very very important. So now we have to consider, so there are these factors like temperature, salt concentration, you have organic fraction, and as well as altitude. So all these are not, these all will not come together to produce a very worst effect, right? So particularly all of these factors have its own significance, but rarely in the nature we find that these factors come together to produce the worst effect in the nature, right? So what is the importance of this DO determination? Now we all know that the river water consists of the aquatic flora and fauna, right? So for this flora and fauna to flourish, there is a minimum level of DO that is required, and that particular DO value is 2 mg per liter. So if the DO value falls less than 2 mg per liter, what will happen? The aquatic flora and fauna will get affected, and the deterioration of this flora and fauna will start immediately. Even I can find out with the help of the DO what I can find out the pollution status of the river. How I can do so? If I'm, let's say, like I'm having a 12-kilometer stretch of river, and I have to find out the pollution status. So let's say at every 5 meter I will be collecting the sample for DO, and I will be finding out the DO value, and I will be getting, so for like I'll be collecting 24 samples, and with the help of the 24 sample I can particularly tell with the help of the DO value where the pollution is more, in which stretch the pollution is more, and in which stretch the pollution is less. So that particular thing can be done, right? DO level of more than 3 mg per liter, but the actual value is 2 mg per liter. Is desirable for the existence and the growth of fish and other forms of aquatic life. So usually in normal flowing water in a very clean river, you get a DO of 6 to 8 mg per liter, right? Next very important use of DO is for maintaining the aerobic conditions in the aerobic biological treatment units. So for many of the many treatment units that we are going to see in our sewage treatment plant, some of the units are aerobic. And aerobic unit will be requiring the oxygen for all the reactions to take place. So with the help of the DO determination, we can find out if enough oxygen is present in there or not, or if there is less oxygen, what can be done. If there is more oxygen, what can be done. So further needful can be done, but the DO measurement, if the DO is present or absent, that can be found out, or if DO is at what amount of DO is present, that can be found out. We are going to find out BOD. We are going to find out BOD values of many samples. BOD is the biochemical oxygen demand. We are going to do the BOD test in next few practicals, and in that the determination of DO is required. So this DO test forms as the basis for the BOD test as well, right? So here I was talking about the pollution status of the river. So when I say that the pollution status, so with the help of a DO, I can only tell that the river is polluted or not, right? But if I have to find out the pollution strength of the river, the pollution strength of the river can be found out with the help of the BOD test, right? Now at this particular juncture, I want to make it clear. So if the value of the DO is less, right? If it is less than 2 mg per liter, the river or that particular water body is said to be polluted. Okay? If it is more polluted, it is extremely polluted water body, the DO value will come as no, it will be coming as a 0 mg per liter. 0 mg per liter means that there is no dissolved oxygen that is present, and that is the worst situation that any water body will face. And that is the polluted, it is the most polluted, extremely polluted water body. So if there are, if the DO value is more than 2 mg per liter, we can say that the fish and aquatic life can sustain in that particular case. But for a fresh water that we require for the drinking, so normally we have to keep the DO in the range of 6 to 8 mg per liter, right? So this is regarding the importance of DO determination. Let's uh, see the DO fixation. So many times what happens is that particularly while determining the DO of a river sample, it is not convenient to carry out the entire DO determination test in the field, right? So that is impossible. So what we will have to do, we will have to collect the sample and we have to do the experimentation in the laboratory. But it may so happen that the laboratory and the site at which we have collected the water sample are far away. So because as they are far away, there is the variation in the temperature as well. There will be some biological reactions that will be continuing when these when we are traveling from the site to our laboratory. So to maintain or to get the actual value of DO, we have to fix the DO at the site itself while after collecting the sample. So how the DO is fixed? The DO is fixed by adding 2 ml of manganese sulfate and 2 ml of alkali iodide azide in the 300 ml of water sample. So if for the best result, we can store it below 10 degrees Celsius, because below 10 degrees Celsius, you do not have any biological reactions that are taking place, and we'll have to find out the DO value within 6 hours only. So this was basics of your DO determination experimentation. Thank you for joining. In this video, we are going to see the process of standardization of sodium thiosulfate. The chemical formula for sodium thiosulfate is Na2H2O3. The commercially available sodium thiosulfate comes in the powder form, and the chemical formula is Na2H2O3 5H2O. So depending upon this formula, we prepare the standard solution of sodium thiosulfate by using the equivalent weight or the molecular weight. The targeted normality for sodium thiosulfate, which is expected in determination of dissolved oxygen, is 0.025 normal. As water of hydration is lost under varying conditions of temperature and humidity, the normality of the sodium thiosulfate will continuously change. So if you have prepared 0.025 normal, the normality of the sodium thiosulfate is going to change, because the water of hydration, that is 5H2O, will lose under the varying conditions of temperature and humidity. Also, the prepared sodium thiosulfate undergoes continuous aerobic oxidation, and the degradation also happens because of the absorption of the atmospheric CO2. So the normality is going to change. So for the best results, what we are going to do is we are going to determine the normality of sodium thiosulfate at the time of titration itself. So this process is called as the standardization of sodium thiosulfate. For the standardization purpose, we require a primary standard whose normality is not going to change with the change in the variation in temperature and humidity. Also, a primary standard do not undergo any aerobic oxidation or a degradation process while it is after it is prepared. So in our case, the primary standard that we are going to use is K2Cr2O7, that is potassium dichromate. Let's understand the procedure of standardization using K2Cr2O7. We are going to take 2 gram of Ki crystals, that are potassium iodide crystals. Potassium iodide is a sublime substance and it will be continuously giving out the iodine. So to suppress this reaction, we are going to add 100 ml of distilled water. Next, we are going to add 10% of 10 ml dilute H2SO4. The H2SO4 available in our laboratory is 36 normal and is concentrated H2SO4. So we have to dilute it and make it and we have to make it to 10%. So we are going to do it in the 10 ml measuring cylinder. We are going to take 1 ml of concentrated H2SO4 and we are going to add 9 ml of distilled water to it. The total volume is now 10 ml and the prepared H2SO4 is a 10% dilute H2SO4. So we are going to add this 10 ml of 10% H2SO4 to the conical flask. Nextly, we are going to add 10 ml of 0.025 normal K2Cr2O7. Normally, we prepare 0.25 normal K2Cr2O7. So here we require the normality of K2Cr2O7 as 0.025 normal. So we are going to dilute the available K2Cr2O7. We are going to dilute it in the same manner as we have did in step number 3. We are going to take a 10 ml of measuring cylinder. We are going to add 1 ml of K2Cr2O7 whose normality is 0.25 normal, and then we are going to add 9 ml of distilled water to it. So this happens to be now 0.025 normal K2Cr2O7 and we are going to add it into the conical flask. Nextly, we are going to add 100 ml of distilled water. This distilled water is added to prevent masking of starch endpoint by greenish trivalent chromium ions. The reaction that now takes place is represented. This is a slow reaction. We'll have to wait for 5 minutes. We'll have to wait for 5 minutes to allow all the dichromate added to react completely to release an equivalent amount of free iodine. So after waiting for 5 minutes and all the amount of iodine is liberated, we are going to add 1 to 2 ml of starch indicator. Now the color in the conical flask will turn blue after addition of starch indicator. The endpoint of the titration process here is blue to colorless. So we'll be now titrating the blue color liquid in the conical flask by using the sodium thiosulfate that we have prepared. We are going to record the titrant required for the endpoint, that is from blue color to colorless. We are going to find out the normality of sodium thiosulfate by using the formula N1V1 is equal to N2V2, where N1 and V1 are normality and volume of sodium thiosulfate respectively, and N2 and V2 are normality and volume of K2Cr2O7 respectively. We already have the values of N2, that is 0.025 normal, V2 that is 10 ml, and V1 that is the volume of titrant required. We are going to find out the value of N1 as by using the formula N2 into V2 divided by V1, which is equal to 0.025 into 10 divided by V1. The value that we have got for the normality of the titrant will be used for determination of the DO value, and we are going to put the same value in the formula. We are going to see the standardization process for our titrant for DO experimentation. The titrant, as earlier said, is
sodium thiosulfate. So the titrant normality that we require is 0.025 normal, and we have prepared our titrant accordingly. In standardization process, we are going to check whether the prepared titrant matches the normality of 0.025 normal. For the standardization process, we require firstly 2 gram of potassium iodide, that is 2 gram of Ki, which we have already weighed on the weighing machine. Now that will be adding to our conical flask. After addition of 2 gram of Ki crystals, we are going to add 100 ml of distilled water. Now this reaction is required to suppress the sublimation of the iodine. We are going to stir the conical flask properly so that all the Ki crystals dissolve properly. Right? After dissolving of all Ki crystals, we are going to add 10% of 10 ml of dilute H2SO4. So what normally we have in our lab is the 100% H2SO4, which is of 36 normal. So what we require in this case is the 10% of 10 ml dilute H2SO4. So what we will be doing is we will be taking the 10 ml of measuring cylinder, will be adding 1 ml of H2SO4 in it, and rest 9 ml of distilled water. So that happens to be 10% of H2SO4. So we require only 10 ml. So we'll be adding 10 ml of 10% dilute H2SO4 in the conical flask now. After addition of every substance, there is the stirring that will be required, right? So stirring shouldn't be missed. After this, we require 10 ml of 0.025 normal K2Cr2O7. So normally we prepare 0.25 normal K2Cr2O7, and similarly we'll be diluting it more to 0.025 normal K2Cr2O7 by taking 1 ml of 0.25 normal K2Cr2O7 and adding 9 ml of distilled water to it. So this we are going to add, that is 10 ml of 0.025 normal K2Cr2O7 in our conical flask. After this, we are going to add 100 ml of distilled water in it. So measure the distilled water properly in the measuring cylinder. We have already measured it, and we'll be adding 100 ml of distilled water into the conical flask. Right? Now after addition of this 100 ml of distilled water, we should wait for next 5 minutes, because the reaction is slow, and it also helps for it helps to take the reaction properly, and it will be, if the reaction is completely done, there is an release of free iodine after 5 minutes. This is a slow reaction, so we are going to wait for 5 minutes. Till that time, we are going to add a titrant in our burette. So wash the burette properly, and the titrant that we are going to add in our burette is 0.025 normal sodium thiosulfate, of which the normality is to be determined. So we are going to fill this burette completely. We have already washed it, and we are going to fill it, and then we are going to adjust it to 0 mark. Yeah, we have done with the 5 minutes, and now what we'll be doing is we are going to add the starch indicator into it. The starch indicator should be freshly prepared, and we are going to add 1 to 2 ml, which is equivalent to 4 to 5 drops of so 4 to 5 drops by the dropper. Yeah, enough. So you will be seeing that a color change will be and you will be getting a bluish color, right? The bluish color is obtained. Now what we are going to do is we are going to titrate this against the sodium thiosulfate in the burette. Yeah, the drop by drop addition of the titrant and simultaneously stirring will be done. The titration should be continued till the colorless sample is obtained. Yeah, the end point of this sample is colorless. So you can see the blue color has changed to the final color, which is colorless. Now we'll be seeing the reading, and the reading that is obtained is, it is 9.3 ml. It is 9.3 ml, and we'll be noting down this reading for our further calculation of finding out the normality. Now we are going to find out the normality by using the formula N1V1 is equal to N2V2. Here N1 and V1 will be the normality of the potassium dichromate and the volume of potassium dichromate respectively, which are 0.025 normal and 10 ml respectively. For N2 and V2, N2 is the normality to be found out, that is unknown, and V2 we have got it as 9.3 ml. So substituting the values, will be getting the normality of sodium thiosulfate. So the formula can be written as N1V1 upon V2 is equal to N2. So substituting the values, will be getting the normality as the normality of the titrant after doing the titration obtained is 0.0268, that is 0.027 normal. So we initially prepared the titrant of 0.025 normal, but due to some error it has come according to the titration process as 0.027, which is to be used finally to find out the DO of the sample.
We are going to see how the DO is determined. We have already seen DO fixation. The need of DO fixation we have already seen. Because of the change in the temperature and pressure at the site and in the laboratory, the DO value may change. So what we normally do is we fix the DO at the site by adding 2 ml of manganese sulfate and 2 ml of alkali azide in 300 ml of water sample. By this particular process, we fix the DO. Again, we'll have to maintain 10 degrees Celsius during the transit, and we'll have to find out the DO within 6 hours of fixation only, right? So let's understand now the DO determination process. The principle here is for estimation of DO content in a sample, an iodide added sample is oxidized under acidic conditions to liberate free iodine. The amount of free iodine liberated is equivalent to the amount of DO originally present in the sample, right? The liberated iodine is estimated by titrating against standardized sodium thiosulfate using starch as an indicate. The amount of free iodine estimated is a measure of the DO in the sample. So let's understand this principle part by part, and then we'll be getting a glimpse of this principle in a whole. So for the determination or for the estimation of the DO content, what we are going to do is we are going to use an indirect technique. we cannot determine the oxygen directly, which is in the dissolved state in the sample. So we are going to use an indirect technique. So in this indirect technique, what we are going to do is we are going to add some iodide into the water sample, and then we are going to make the iodine liberate into that particular sample, right? So how we are going to add the iodide here? We have added the alkali iodide azide. So this particular 2 ml of alkali iodide azide is will be helping us to make this sample as an iodide added sample, right? We are going to oxidize it under the acidic condition. How we are going to provide an acidic condition? We are going to add 2 ml of H2SO4, that is concentrated H2SO4, and that will be providing the acidic condition. So when the iodide sample is given an acidic condition, the it get oxidized, and when it get oxidized, it liberates the free iodine. So we are going to measure this free iodine, and the free iodine measured is nothing but the DO in the sample. So the free iodine that is getting liberated, we are going to measure it with the help of the titrant called as sodium thiosulfate, and with that particular technique or titration technique, we are going to find out the DO. Right, for that particular purpose we required the apparatus as burette. For the titrant we'll require pipettes for sodium thiosulfate, alkali. We require pipette for magnesium sulfate and alkali iodide. We require BOD bottles, that is 300 ml BOD bottles. We require conical flask, thermometer for measuring the temperature of the sample. We'll be requiring the chemicals magnesium sulfate and alkali iodide, which are used for the DO fixation. Concentrated sulfuric acid for providing the acidic condition. We here have a starch as an indicator, and the color of starch indicator is it is a liquid and it is colorless. And for the titration purpose, we are going to use sodium thiosulfate, which has a normality of 0.025 normal. Procedure of a test. The very first take is take a 250 ml of a reagent bottle or 300 ml of BOD bottle, and we'll be filling it completely with the sample. We are going to tap the bottle all around to release the entrapped air bubbles, and then we are going to record the temperature. After recording the temperature, we are going to stopper the bottle. Nextly, we are going to remove the stopper and add 2 ml of MnSO4, that is manganese sulfate, using pipette, dipping the open end of the pipette below the liquid surface. Right? After adding 2 ml of MnSO4, we are going to add 2 ml of alkali iodide acid using a pipette. Now this is nothing but the DO fixation process. If you have fixed the DO at the site, which is recommended, there is no need of doing or repeating this process in the laboratory, right? So it is only to be done once. If you have done or fixed the DO at the site, I'm repeating again, there is no need of doing DO fixation in the laboratory. If you haven't done at this site, then this DO fixation is will be the first step that we are going to do in the laboratory. So if the DO is absent, what will happen if the DO is absent? That whole bottle will get a white PPT, and that PPT is of manganese hydroxide, right? So manganese hydroxide is formed, which has a white color, and that particular white PPT suggests that the DO is absent. Now, where the DO will be absent in a very polluted sample, normally the DO will be absent. So if you have a very polluted sample, the formation of manganese hydroxide is there after adding of 2 ml of MnSO4 and 2 ml of alkali iodide. That is, immediately after DO fixation, you will be getting a white PPT if the DO is 0. That is, it recommends that the DO is 0 and the sample is very, very polluted, right? So the experiment can be stopped at this particular stage. Why to stop? Because we have already got the value of DO. The DO value is 0, and that you can put in the observation table. There is no need of calculation to be done, right? So DO is 0. But now what happens if the DO is present, right? So if DO is present, manganese ions are oxidized to magnetic anions, and a brown PPT of manganic basic oxide is formed, right? And this has a brown PPT. So you will be getting a brown PPT if the DO is present. I'm repeating again. If you have a DO absent, there will be a white PPT of manganese hydroxide form. If the DO is present, there will be a brown PPT of manganic basic oxide that will be formed, right? So if the DO is absent or if you get a white PPT, you'll have to stop this experiment at this particular stage only. If you get a brown PPT, you'll be continuing the experiment and move towards the next step. So what we are going to do, if there is a brown PPT formation, we'll be stopper the bottle and mix by inverting the bottle several times, right? So we'll be shaking the bottle or we'll be turning it upside and down and will be mixing the content in the bottle properly. After that, what we are going to do is now we are going to remove the stopper and add 2 ml of concentrated H2SO4, that is sulfuric acid, which has a normality of 36 normal. A measuring cylinder is used for adding the acid. You do not add acid with the help of the pipette, right? You will be adding the acid with the help of the 2 ml, 100. You're going to add the concentrated H2SO4 of volume 2 ml by using the 10 ml measuring cylinder. Nextly, what we are going to do is topper the bottle and mix the content by inverting the bottle several times until the brown PPT gets completely dissolved to get a uniformly yellow colored free iodine solution, right? So previous brown PPT what you have got, after adding the 2 ml of concentrated H2SO4, this all will dissolve and you will be getting a uniformly yellow colored free iodine solution. Under acidic conditions, manganic basic oxide oxidizes iodine to free iodine. So if you remember the principle, after the in principle we have seen the iodide added bottle after we give the acidic conditions liberate free iodine. So here also the iodine is liberated. The process, the reaction that take place is here, and here you can see this I2, that is nothing but the free iodine. What we are going to do is next is the take 203 ml of iodine solution in conical flask. The extra 3 ml is the correction for 4 ml of reagents added to DO fixation. So this is very, very important, right? So 3 ml, why the extra 3 ml is taken? Normally it is recommended to take, normally we would have taken 200 ml. So, but here they have told us to take 203 ml. Why so? The extra 3 ml is the correction for 4 ml of reagent. 4 ml, that means that 2 ml of alkali iodide and 2 ml of manganese sulfate that we have added previously, right? Titrate against standardized sodium thiosulfate Na2S2O3 of 0.025 normality using 1 to 2 ml of starch as an indicator. So after taking 203 ml of this yellowish color solution in the conical flask, we are going to add starch indicator. How much? It is 1 to 2 ml. How we are going to measure this 3 ml? 3 ml of uh, this solution is to be added with the help of again measuring cylinder only. Do not use pipette unless your pipette has a blower, right? Now next thing is that we have taken 203 ml of iodine solution, that is yellow colored solution. We have added the 1 to 2 ml of starch indicator. Now you will be seeing that after addition of 2 ml of starch indicator, it will turn blue, right? So at this particular stage, what will happen is that um, all this free iodine, which is an oxidizing agent, is reduced to iodine, and sodium thiosulfate reducing agent is oxidized to sodium tetrathionate. So this is how the titration process will happen. So the blue color liquid is now to be titrated with the help of the sodium thiosulfate, and it will be the redox reaction that will be happening. Free iodine, which is an oxidizing agent, is getting reduced to iodine and sodium thionate, which are the reducing agent is oxidized to sodium tetrathionate. Now the reaction is there in front of you. We'll have to stop the titration when the blue sample turns into colorless. We'll be recording the amount of titration that will be used, and we'll be putting it into the formula to find out the DO value. there is a note that is written: after some time, absorption of atmospheric oxygen liberates more free iodine, which reacts with starch to give it a blue color again. Further use of titrant to reduce this blue color will give an erroneously high DO value, which is to be avoided. So after your titration is finished, that is that you got a colorless sample in the conical flask. If you keep it for some time, the absorption of atmospheric oxygen again takes place, and no, because of that, again you will be getting blue color. But we don't have to titrate it again, because that will be giving you a very high DO value, right? So we'll be using, we are going to record X ml, that is the ml that is required to for the disappearance of the first disappearance of your blue color, and we are going to note that, right? So here we have used the starch as an indicator. So why, what is the action of starch as an indicator? Starch is an absorption type of indicator. During titration of iodine with sodium thiosulfate, addition of starch results in the formation of weak blue complex due to adsorption of iodine on colloidal starch particles. As iodine is extracted and reduced, and the intensity of a blue color gradually decreases. When all the free iodine is reduced to iodine, the blue color totally disappears, and this indicates the end point of the titration. We are going to calculate the DO in the sample by using the formula. For the formula purpose, please refer the next video.
We are going to see the DO determination experimentally. We have taken two samples. One is the sample that is collected from the tap water, and another is a sample which has a very high organic content, and you can see the color is blackish, right? So we have tap water and a very blackish water which has a very high organic content. So the very first step in our experimentation is to fill the sample in the reagent bottles, right? So we have 300 ml BOD bottles, and we are going to fill the sample in both of these bottles. This is the tap water. We are going to stopper that bottle. The excess water sample will flow out. It's okay. Next BOD bottle, and we are going to fill it with the help of the blackish sample. We'll have to stir it properly so that a uniform sample is getting filled in the bottle. You can observe the color of the sample that we have. It contains a very high organic load. We'll be stoppering this bottle. Yeah. The excess sample is drained off. Now we are going to measure the temperature with the help of the thermometer of both the samples. So we'll be removing the stopper and measure the temperature. The ambient temperature of a lab is 22.6. Here we get the temperature as it is 25 degrees Celsius. We're going to measure the temperature of the second sample as well.
25.
And approximately we'll be getting the same temperature. Alright. So now what we are going to do is we haven't fixed the DO at site, right? The sample were collected from tap, and this was a laboratory made sample with a very high organic concentration. So we are going to fix the DO, and the DO is fixed with the help of 2 ml of manganese sulfate and 2 ml of alkali iodide azide. So using two separate pipettes, what we are going to do is, we are going to firstly add manganese sulfate in both of these BOD bottles, and then we'll be adding the alkali iodide azide. Firstly the manganese sulfate, 2 ml in each bottle. We have added 2 ml of manganese sulfate in both of these bottles. With a separate pipette, we are going to add alkali iodide azide. The volume is 2 ml in both of the BOD bottles. Please see the change in the color that is happening after addition of alkali iodide azide. So first, in tap water you can see the yellowish or brownish PPT that is formed, and another bottle which has a very high organic concentration, you can see there is a whitish PPT that is formed. After putting the stopper, we'll be turning the bottles upside down properly with utmost care. You can turn the bottles upside down here, and you can see the brown PPT, and here you will be seeing there's a blackish content, but initially you can see there is a whitish PPT that is formed, which is not yellow in color. There is a white PPT that is formed initially you have seen, but now because there is a high organic content and there is a blackish color to this sample, here we got the black color, but you will be seeing in the bottle. Can I get the bottle? Second bottle? Yes. Yeah. So here you can see there is a whitish liquid that is getting formed. So it is not an yellow PPT, right? So here you have a yellow PPT or a brown PPT where the DO is present, and this kind of color, that is a whitish color, will be obtained when you will be having the zero DO. So as the color sample color is black, so particularly you are not getting that white color properly, right? So what we are going to do next is that with our first bottle where the white PPT has formed, so the DO is absent because we got a white PPT. So we are not going to find out the DO of this bottle, right? So we already got the answer. The DO of this bottle is 0 mg per liter. Now we are going to focus on the second bottle for which we have got the brownish PPT, right? So the next procedure is we have to give the acidic condition for the free liberation of iodine. So we are going to add 2 ml of concentrated sulfuric acid in this bottle. Please note down the reaction that is happening. You can see a turbulence that is created in that bottle. We'll have to shake this bottle properly, and all this brownish PPT will get dissolved, and you will be getting a uniform yellow colored liquid. Yes, this is the uniform yellow colored liquid that you have got And here at this particular juncture there is the process of free iodine liberation that is taking place. Now next step is we have to take 203 ml of sample take 250 ml of measuring cylinder and measure 200 ml properly. It should be properly taken so that no turbulence is created, otherwise the turbulence will add excess of oxygen. So fill the cylinder properly to 200 ml. We have got 203 ml of sample for the determination of DO. Now this is the oxidized DO sample that we have got. There is the iodine is liberated, and now we are going to measure this iodine with the help of the titration process. So the next step is addition of 1 to 2 ml of starch indicator. We are going to add it with the help of the dropper. You can show the starch beaker. Yeah, you can see the color change. It has turned blue. Check it well. Yes. Akshay, please show the starch indicator beaker. Yeah. Yes. This is how the starch indicator looks like. Now you can see the bluish color that is obtained slightly on the higher side. This is the bluish color that is obtained slightly on the higher side. Now we are going to titrate this against the sodium thiosulfate that we have prepared, and the end point is colorless. Akshay, can you remove the measuring cylinders? Yeah. Drop by drop addition and simultaneously shaking of the conical flask is to be done. Note the color change. Here it is turning to slightly colorless red. It was faint blue. Now you can see it has turned totally colorless. So we started with a blue color. Then we got faint blue color, and now this is totally colorless, and this has obtained for the reading 5.9 ml. Right? So this is the entire titration process that we did. So now we have got the value of X, which is to be put into the formula for finding out the DO value.
Let's see the calculation part for the determination of the dissolved oxygen. For standardization, we have already seen, but I am repeating here with the values. So we got the value of V1 as 9.2 ml. By using this value, we are going to find out the normality by putting it in this equation. So if we get the normality as 0.027 normal. So we have prepared the sodium thiosulfate with 0.025 normality, but due to the variation in the temperatures, pressure, the aerobic oxidation and everything, we have got it as 0.027 normal, and same will be using in the calculation of a DO. So the formula for calculating the DO in mg per liter is given as this. So we required ml of titrant used into normality of the titrant into equivalent weight of oxygen into 1000 divided by ml of sample taken. So for substituting the values, we got 5.9 as the value of x, 0.027 as the normality, 8 is the equivalent weight, and 1000 is the the value that has to be taken for the conversion for mg per liter. Here you can see the ml of sample taken is 200 ml and not 203 ml. 3 ml was just for the correction. Here for the calculation purpose we are going to take 200 ml. So if substituting the values, we get the value of a DO as 6.37 mg per liter. We are also going to find out the values of different samples. But firstly, let's focus upon the sampling and the testing details as well. Location of sampling, we have collected it from environmental engineering lab only. Sample collection date is 27/8/2020. We have collected the sample at 10 a.m. The type of sampling was graph sampling, and the person who's collected the sample was Mr. Akshay Kanse. Sample received in the lab, same date. We have did the analysis on the same date, and again, the name of the testing person is the Mr. Akshay Kanse. If you have to submit the report, you can even write the report number here. So these are the details that normally recommended to follow for collection of the sample and collection and the testing of the sample as well. This is the observation table. We have considered few more sample. Here, the description of the sample is given. Inlet of the STP. STP means the sewage treatment plant. Outlet of the STP, that means the uh, treated water coming out through STP. And there also we have taken the hot tap water. We have did the analysis. The temperature and the volume of the titrant that was required is given here. We have to find out what is the DO mg per liter, and then you are going to put a remark with respect to whether it is more than 2 mg per liter or less than 2 mg per liter. If it is the DO value comes out to be more than 2 mg per liter, the DO is sufficient and the aquatic life can sustain. If it is less, then the water sample is polluted and the aquatic life is not sustained in that sample. So the remark in that format is expected. There are also some important questions with respect to the oral that depend upon the understanding. So the oral questions are given here. I've also uploaded the material that you required to read, that is the extra reading material, which is from where the most of the questions in the oral can be asked.